Okay, so let me start. So today, this is sixth lecture of my advanced nuclear physics course. And so far I have discussed some microscopic descriptions for nuclear many-body problems, especially finite nuclei and excitations and some reactions. And in the rest of two lectures, I will introduce some physics of neutron stars and applications for those physics. I mean, different from the finite nuclei. So today I will explain how nuclear physics is connected to the physics of neutron stars, starting from the nuclear force. Actually, we can derive the so-called equation state, and which is directly connected to neutron star structure. Okay, and okay. So, as I mentioned, so in this lecture, I will introduce some introduction to the neutron star physics. And in the last lecture, I will explain some specific topic, especially related to the neutron superfluidity inside the neutron star. So we have some observational evidence of existence of superfluid neutrons, and which is called pulsar glitches. Okay. So today I will focus on this subject. Okay, so purpose of today's lecture are following. So first I will present an overview of structure of neutron stars. So what's inside actually the neutron star. And I will explain how a variety of phases emerge depending on the density. So depending on density or pressure or depth from the surface, we have abundant exotic phases of nuclear many-body problem, and I will introduce some of them. Okay. And then, so as a specific application of PDDFT, I will introduce some recent attempts to describe some neutron star crust, so which has some properties of solids, like a solids, and we apply band theory based on TDDFT to describe this system. Okay, and this is the main goal. So to understand how structure of neutron stars can be understood as a microscopic quantum many-body problem. So starting from nucleons, based on the mean field approach, we can describe many properties of neutron stars. Okay, so this slide was used in my first lecture. So far we have explored the planet of finite nuclei. So we started from the continent of stability, let's say, and we are sailing towards the edge of the nuclear landscape. So we are sailing on the sea of unstable nuclei. And theoretically, we can imagine anything. So we can imagine to gather really a lot of neutrons. And in such a case, the gravity makes the attractive force, and we have bound object. So in this lecture, we will leave from this planet of finite nuclei. And I will introduce the physics of neutron stars. So how it is connected? So this first part is already shown in my first lecture, so I will go quickly. So this is one typical example of the star, shining star. So this is the sun. So and the energy source of this object is actually the nuclear fusion reactions. So inside the massive star, we have some nuclear reactions, which is occurs through the quantum tunneling. So we have some nuclear reactions. So when we consider this kind of heavy massive star, then nuclear physics comes in. So in case of the star, the so-called PP chain happening. So in PP chain, the 4 protons react each other, and in the end, we have formation of helium-4 alpha particle. And the point was the masses of those systems before and after reactions are different. So before the reaction, it is heavier than after the reaction. So this is due to the binding of neutrons and protons. So according to this equivalence between energy and the mass, and we have the energy corresponding to this binding energy or loss of the nuclear mass. And this reaction occurs through the quantum tunneling. So it means that stars have finite temperature. So those atomic nuclei have some kinetic energy, but it is much below, far below the Coulomb barrier. So they cannot fuse classically. But through the quantum tunneling, the tail of the wave function penetrates through the Coulomb barrier, and with tiny probability, the nuclear reaction happens. Okay. And that was related to the stability of finite nuclei. And as I mentioned in my first lecture, here is the most stable nucleus, ion 56. So it means that the lighter nuclei can gain energy by nuclear fusion reactions. So like a PP chain, we have chain of reactions until formation of the ion 56. On the other side, the heavy nuclei can gain energy through the nuclear fission. So after the fission, it can gain the binding energy, and the mass is reduced and energy is emitted. So inside the star, the fusion reaction happens for until ion 56. But as I introduced in my first lecture, so it is not easy. So I just reminded this subject. So you may naively consider the fusion of 2 alpha particles that can form beryllium-8. But the beryllium-8 is unstable. It decays in 10 to minus 17 seconds. So this reaction path cannot be used to synthesize more heavier elements. So instead of this, we may add some proton and 1 proton or 1 neutron to alpha particle. But those nuclei with mass number 5 are both unstable. It decays actually in 10 to minus 22 seconds. So this is also not the reaction path. The point was, yeah, we have some kind of resonance, the so-called Hoyle state, in the carbon 12, in the excited state, which has some cluster structure. Since this cluster structure, this cluster state has some energy below, near the threshold of 3 alpha particles, it can form through this triple alpha reaction. And this kind of resonance and triple alpha reaction was suggested or predicted by Fred Hoyle. And later, experimentally, this excited state was discovered, actually. And this kind of nuclear structure with clustering is one of the hot topics of nuclear structure study. And yeah, let me just remind you that, mention that, with Hartley-Fock approach, we have one single mean field potential, and we put some neutrons and protons. This is like a shell model picture. But it is actually difficult to describe this kind of clustering state. And in such a case, we may superpose many Slater determinants and re-diagonalize the Hamiltonian. And by doing so, we can expand the model space or flexibility of wave function, and we can get this kind of cluster state actually. But this is beyond the scope of this lecture. So anyhow, so this is the life cycle of light star. So yeah, those interstellar gas are gravitationally accumulated, and at some point a star is formed. And then inside the star, we have chain of reaction like PP chain. And in case of more massive star, we have more fusion reaction like carbon and oxygen formation through the CNO cycle and triple alpha reactions, something like that. And in case of this kind of light star, it cannot go further. So after formation of this kind of carbon or oxygen core, the fusion reaction stops and it gradually decays into planetary nebula or gravitationally collapses into the white dwarf. Okay, so let me just say a few words about what's inside of the white dwarf. Okay, so what is white dwarf? So here, as you can see, this is the Earth, and this is just an image of white dwarf. So as you can see, the size of white dwarf is similar to the Earth, size of the Earth. But the mass is different. The mass is like a star. The solar mass is squeezed or put into this smaller, much smaller size. So if we write this mass and radius relative to the solar mass, the radius and mass of the sun, and then you can see the mass is like a sun, like 1.3. It can be a bit lighter, but it is similar to the solar mass. But the radius is much, much smaller than the sun. Okay, and it is like a Earth. And inside the white dwarf, we have no fusion reaction. So fusion reaction has been stopped. And the gravitational force is sustained by the electrons' degeneracy pressure. Okay. And then inside of the white dwarf, we have some of crystal Coulomb lattice of nuclei. So it is something like this. So outside of the white dwarf, we have some gas of helium and hydrogen. And inside, I mean, inner part of the white dwarf, we may have some Coulomb lattice, like a crystal of carbon or oxygen nuclei. And the elements are depending on the mass of the progenitor. So what was the star that decayed to the white dwarf? So in case of lighter star, only helium nuclei can be there. But in case of more massive star, we may have those elements that are synthesized through the fusion reaction before the gravitation collapse. Okay, so this is just a comment on what is inside of white dwarf. Okay, yeah.
What if it's like less than 0.17?
0.1?
What happens to a star if it has less mass than the sun? Does it become, if it's less than that?
Probably it cannot go to white dwarf.
Right, it just becomes what? Dead, just
Dead. Yeah. Yeah, it somehow spreads and decays. So it cannot collapse, probably. I'm not so familiar, but yeah, it cannot go to this way. And here I just mentioned, yeah, in case of binary system with white dwarf and some other red giant or some star, some matters can be transferred from one star to this white dwarf, and in case where this mass exceeds the so-called Chandrasekhar limit, about 1.4 solar mass, it can collapse. But gravitationally, I mean, the electrons degeneracy pressure cannot sustain the gravitation force, and it undergoes the so-called type 1a supernova. And it can go form a neutron star. This is just to mention. Okay. So in case of massive star, we can have more fusion reactions heavier than oxygen region. And yeah, eventually we will have a formation of ion core. So after the formation of ion core, the pressure and temperature decreases, and it can no longer sustain the gravitation force, and it collapses into the supernova. Okay. So after the supernova explosion, we have formation of black hole in case of very massive star. But if mass is not so heavy to form a black hole, we will have a formation of neutron star. And this neutron star is, in our nuclear physics point of view, ultra heavy super neutron rich nucleus. And we enjoy to study this object. So we can apply the same technique, the microscopic approach based on nuclear many-body problem, and we can study variety of properties of neutron star. Okay. And yeah, in the following, I will introduce some specific parts of neutron star. So what's inside? And this is, yeah, some cross section of neutron star showing several layers depending on the density and pressure. And yeah, I'd like to mention here that, okay, so this inside the neutron star, we have low density region at the surface, but as we go from the surface to the deep inside of neutron star, the density increases and it can exceed the nuclear saturation density. So we have a range of density regions inside the neutron star which cannot be studied with terrestrial experiment. So it is a great playground for nuclear physicists. Okay, and yeah, in the outermost layer, we have kind of hot plasma. So it is just a plasma of some gases. But when we go into the neutron star a bit, we will have a formation of Coulomb lattice, which is called outer crust. So in this case, actually, first of all, we have formation of ion, the most stable nucleus. So atomic number 26. And yeah, they form a Coulomb lattice, like a solid in the terrestrial matter. And as we go from the surface to the bottom layer of the outer crust, the density increases. And with the density, electrons' chemical potential increases. So energetically, at some point, the system, I mean, this neutron star prefers to convert these electrons to be captured by protons and the neutrons, the number of neutrons increases. So the matter becomes more and more neutron rich as we go into the deeper layer of outer crust. Okay. And the size, I mean depth, is about several hundred meters. And at some point, as I mentioned, the number of neutrons increases, and at some point, neutrons start dripping out of the nuclei because we have some drip line of finite nuclei. So in this layer, the so-called inner crust, we have Coulomb lattice of nuclei, and outside of it, we have a sea of superfluid neutrons. Okay. So such a system with solid crust with permitted by the neutron superfluid is called inner crust. And when, if by going more and more deeper side of the inner crust, the density increases and the lattice constant or spacing between two nuclei decreases and decreases further and further. And at some point, it becomes merging, I mean melting, and it becomes a uniform matter. So here is this region. So we have uniform matter of neutron, proton, electrons, and muons, and which is called the outer crust. Outer core, sorry, outer core. Okay. And this outer core is just a uniform nuclear matter, and it is simpler, much simpler. And by going further, as I will explain later, we will have more exotic particles like hyperons, which contains strange quarks, or some meson condensate, or formation quark matter. And this region, which is not well known actually, is called inner crust, inner core, sorry. So there are those crust region, which is like solid, and those core region, which is like gas, nuclear gas or nuclear liquid. Okay. Okay, so this is just a global view of what's inside the neutron star. So, okay, let's go let's look more carefully what is going on in the crust region. So in an outer layer of or low density region of neutron stars, actually nuclear matter is not homogeneous or uniform. Okay, the reason is because of the nuclear interaction or nuclear force, which is attractive. Neutrons and protons are clusterized, like formation of finite nuclei, and they form a Coulomb lattice. It is more energetically favorable. So you can imagine some gas of neutrons and protons and make it dilute, and then instead of distributing everywhere dilutely, the system can prefer to form a nuclear to gain a binding energy. And also they form some kind of lattice structure to reduce the Coulomb energy. So it is like a crystal or solids. Okay. So now let me explain what inside the outer crust and the inner crust. So first of all, I'd like to show, some, what nuclei are emerging in outer crust region. So again, so this is the cross section of a neutron star, and this is just an image which I explained. So we have some lattice of nuclei, which is believed to have BCC, body-centered cubic structure, and around this nuclei, we have relativistic electron gas, making the system electronically neutral. And actually, we can calculate very easily what kind of nuclei emerges inside the outer crust region. So to this end, what we should do is to minimize the Gibbs energy as given here. Okay, so I'm not going to the detail, but this second term contains the lattice energy, which is associated with this formation of this Coulomb lattice. And this second term in the parenthesis is the 0-point energy, which is a 0-point oscillation of those Coulomb lattice. And the third term here is just the electron's chemical potential. So this second term here is well known. It is just the Coulomb lattice, energy of Coulomb lattice and electron's chemical potential. So the important ingredient of this Gibbs energy is just the first term. And this M prime is nothing but the nuclear mass. Okay. So if we have a mass model or experimental masses, we can use this information to calculate this Gibbs energy for various neutron and proton numbers and minimize this. And we can get the elements, I mean the composition of outer crust in this way. So, okay, starting from the surface to the bottom layer of the outer crust, okay, it is about a few hundred meters. We have variety of nuclei appearing in the neutron outer crust of neutron star. In the low density region, we have indeed formation of ion 56, the most stable element. But as we go down, the number of, neutron richness increases, and together with the number of neutrons, the number of protons also increases. Okay, and we have those nuclei with atomic number 26 to 30, 40, 42, or something like that. So those nuclei are forming a Coulomb lattice inside the outer crust. Okay. So, and actually it is probably difficult to see, but those nuclei with thick characters, thick fonts, as you may see, those are experimental masses are known. So actually those elements are well constrained, or those are really emerging in the outer crust probably. And in the neutron-rich region, we have some nuclei without experimental masses. In such a case, we need to employ some theoretical mass models, like Hartree-Fock or HFB or some kind of other mass models. But anyway, using some information on nuclear masses, you can easily calculate those elements inside the outer crust. Okay. So the next one is the inner crust. So in the inner crust, in addition to the Coulomb lattice of nuclei and the surrounding relativistic electron gas, we have a dripped neutrons. Okay. So this is the case. And this is an example of a seminal paper published in 1978. So I think this was the first paper using the Hartree-Fock approach to describe the inner crust structure like this. Okay, so this upper part is low density region close to the outer crust, and the lower part is close to the transition from the inner crust to outer core. So as you can see, the spacing between two nuclei or lattice constant, or the distance between neighboring nuclei is decreasing with increasing the density, as you may imagine. And by going from the lower density region to higher density region, as you may see, okay, so these two lines corresponds to proton density distribution and neutron density distribution. And because the number of neutrons is increasing, we have, as you may see here, the drift neutrons outside of that cluster. Okay. And this cluster or nucleus is somehow melting. The surface becomes more and more diffusive as we go down deeper side of the inner crust. And eventually it becomes uniform in the outer core region. So using density function theory or Hartree theory with effective interaction, we can calculate this kind of structure in the inner crust in this way. Okay, so those are, that's the structure of outer crust region of neutron star. So now I will explain how to calculate the structure of neutron star from the okay. Before the structure, I will explain what determines the composition. Composition means we have electrons, muons, protons, and neutrons in the outer core region, and the ratio is depending on the density. So how we can determine those compositions? So actually it is the so-called beta equilibrium condition and charge neutrality condition. Okay. So I will explain here nicely. So okay, so this is just I just remind you about the beta decay. So I took this slide from the lecture 1. So what I mentioned here is, okay, so this is the mass parabola, or so the horizontal axis corresponds to the mass, or if we go down below, the binding energy, when binding energy becomes larger, we have more stable nuclei, and it reaches this the minimum of the parabola. So through the beta decay, beta minus decay or beta plus decay, those nuclei try to become more stable nucleus. Okay, so those are beta minus and beta plus decay. And naively thinking, it is related to the neutron and proton chemical potential. So in case of neutron-rich nuclei, we have more higher Fermi energy for neutrons. And in such a case, by converting a neutron at the Fermi level to the one proton, to the beta minus decay, the system becomes more stable. And by the way, because of the Coulomb repulsion, this potential is somehow shifting upwards. But anyhow, so in this way, system try to reduce the energy through the beta decay in this kind of example. Okay. So this is just an example of beta decays in finite nuclei. But we can apply this, this way of thinking to see what appears in the inner or neutron stars. Okay, so I will explain step by step. So let's assume that we have only neutrons, okay, no electrons or muons no protons, so only neutrons. Such a matter is called pure neutron matter, PNM, pure neutron matter. So in this case, by writing chemical potential in this axis, and yeah, with rest mass energy, yeah, it is about 940 MeV. Okay. So we have this, and by adding the chemical, by adding the Fermi energy, kinetic energy due to Fermi motion, we have this additional energy. So this is the summation of rest mass energy and this kinetic energy. And here I will neglect the interaction to make the situation simpler. So only I here only consider the kinetic energy. Okay. So in case of pure neutron matter, as you may see, this because of the Fermi energy, yeah, we have the system it has higher energy. Okay. But okay, so similar to the beta decay in finite nuclei, you may imagine, okay, so the neutrons may decay through beta minus decay to form the protons to make Fermi energy similar. Okay, so now we consider the symmetric nuclear matter. It is the matter, nuclear matter with the same number of neutrons and protons. Okay. So in this case, we have beta minus decay, and okay, so this is the rest mass energy, which is very close to the neutrons one, and we have this kinetic energy of protons. Okay, but in this case, it is problematic because of the Coulomb interaction. So now we only consider the neutrons and protons, the same number of neutrons and protons. And in such a case, in infinite system, the Coulomb energy is divergent. So this is not true. So what we should do? So fortunately, we have negatively charged particle, namely the electrons. So we can we can distribute the electron gas of the background electron gas together with neutrons and protons. And we require the charge neutrality condition. Okay, so this is the requirement of number density of protons and electrons must be the same to make the system electrically neutral. Okay. So now we have electrons, but please be careful that the electrons' rest mass is much smaller than those of neutrons and protons. It is just a 500 keV. So rest mass energy is somewhere here. And we have electrons' kinetic energy, Fermi energy, determined by this condition. Okay. And we require the so-called beta equilibrium condition. It means that the chemical potential of neutrons here must be equal to the sum of protons and electrons' chemical potentials. It means that we have some equilibrium of beta decay. So the system cannot gain energy through the beta decay or beta plus or minus decay. So this is the equilibrium condition together with this charge neutrality condition. So in this way, we can predict the composition or ratio of number of neutrons, protons, and electrons inside the outer core, the uniform nuclear matter. But this is not the end of the story. Okay. Okay, so here I'd like to mention one thing. So you should, when you consider the electron gas in the inside the neutron star, you should use the relativistic formula. Yeah, you cannot neglect the relativistic effect. And this figure indicates the importance of relativistic effect. So if you apply just the non-relativistic formula, as given here, for electron gas, okay, since the electron's mass is much, much smaller, so this, in the denominator, you have much smaller value for electrons. So if you apply this, simply, then you have this kind of much larger Fermi energy. But if you apply relativistic formula, actually the energy becomes much, much smaller than non-relativistic one. So naively thinking non-relativistic way, you may imagine the kinetic energy of electrons is 2000 times of that of protons because of this change of the mass, but it is not the case. So relativistic effect is very important to correctly describe the electron's chemical potential here. And on the other hand, here I plot the comparison between protons' chemical potential and the relativistic one and non-relativistic one. So in case of nucleons, the relativistic effect is very small. We can neglect it. It is due to the fact that we have much larger mass as compared to electrons. So this is just to remind you the importance of relativistic effect for electron gas. Okay, so now, yeah, we have learned what is beta equilibrium condition and charge neutrality condition. So, but the situation can be changed further. So if we go higher in density, then this chemical potential of electrons grows. And at some point, it can exceed the rest mass of mu. In such a case, okay, so it is actually about 106 MeV, so it is relatively light. And when electrons' chemical potential exceeds this rest mass of muon, then it can decay. I mean, by decaying electrons, by converting electrons to mu minus muons, we can reduce the chemical potential. Okay. So in this way, new particle emerges. And we have another beta equilibrium condition for leptons, electron and muons. The equilibrium condition between those two particles. And the charge neutrality condition becomes this way. It is just a naive extension of this because the muon has negative charge. Okay. So far you have, okay. In this way, you can understand what is inside the outer core region, the uniform nuclear matter. Now, here is a debatable unsolved problem, the so-called hyperon puzzle. Let me introduce this. So, yeah, the situation changes again if we go higher in density. So you may consider what happens if we go further in density. So more higher density region, what happens? Then the chemical potential or Fermi energies of neutrons and protons increases and more and more. And at some point, actually, it can exceed the rest mass of other particles, other hadrons. For instance, the lambda particle. The lambda particle is composed of up-down strange quarks, and its rest mass energy is 1,160 MeV. So it can, the neutron's chemical potential can exceed this value, and then again, we will convert the neutrons into lambda particle to reduce the total energy of the system. And we will have this condition. Since this lambda particle is neutral, charge neutral, we will have this condition between neutron and lambda particle. And yeah, this is a problem. So naturally, naively thinking, if we go higher and higher density inside the neutron star, this kind of new particle must emerge. And EOS equation state will be changed. So this is the problem. So based on some calculations, we can calculate what kind of particles emerge as a function of density. So this figure shows the particle fraction as a function of the number density of baryons relative to the saturation density. So in the lower density region, up to, let's say, 2 times saturation density. So those are outer core region. In such a case, this black line, these neutrons are, yeah, almost 1. But we have some fraction of protons. Through the delta equilibrium condition and charge neutrality condition, yeah, we can determine those fractions. But at this region, around 2 times the saturation density, actually sigma minus, lambda, and sigma 0, blah, 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 emerge according to this calculation. Okay, and the problem is when we introduce new particles, then the EOS equation state becomes softer. So soft means it can be more easily compressed. So it makes the mass radius relation of neutron star more, how to say, smaller, or the maximum mass becomes much smaller. So here I show this in this figure, I show the mass of neutron star as a and the relation with the radius of neutron star. So using one equation state with this kind of particles, we can calculate what will be the mass and radius. So relation between mass and radius for this neutron star. And when we consider pure neutron matter, PNM here, it goes like this, with maximum mass about 2.4 solar mass. But by introducing, okay, in this case, lambda particles, probably the equation state becomes much softer, and the maximum mass is significantly reduced. Okay. And the problem is, observationally, we know that there exists the neutron star with the mass close to the 2 times solar mass. So to explain this observation, the equations of state can sustain at least 2 times of the solar mass. But when naively one introduces the hyperons, it becomes difficult to sustain this 2 times solar mass neutron star. Okay, so it is the so-called hyperon puzzle. So naively, again, yeah, there should be some new particles in higher density region when we consider the energetics between those particles. But by introducing those particles, it will be difficult to explain this 2 times solar mass neutron star. And one should, for instance, study the forces, interaction between hyperon and nucleons, like hyperon, and those are 3-body force, which was discussed probably by Sekiguchi-san in the first part of the lecture. So we know that the 3-body nuclear force is important between nucleon, 3 nucleons. It makes equation state much stiffer and we have saturation properties. And yeah, there are some discussions by introducing such repulsive 3-body force, including hyperons, we can reproduce or explain this massive neutron star, even if it includes the hyperons. And this kind of study is, for instance, related to the work in Fujioka-san's group. So he's an experimentalist. And also Sekiguchi-san's study is also related to 3-body force and yeah, relevant to this kind of problem. Okay. Yeah, and those are still open problems. And one can consider, for instance, the transition to the quark matter. And in such a case, there may be no problems with this kind of soft drilling, but we don't know yet. So this is just an open problem. So now I will explain how to understand the neutron star structure starting from the microscopic nucleonic degrees of freedom. Okay. So I will explain starting from the nuclear force, how to describe the neutron star structure. So now I will introduce the equation state, which I already mentioned in this lecture. So the equation of state is just the relation between energy and the density. So here I plot the energy per particle as a function of density, baryon density. Then in case of pure neutron matter, which is composed of only neutrons, we have this kind of density dependence. And for symmetric nuclear matter, we have this kind of behavior. And yeah, we have many parameters to characterize those equation states. And especially, we have those parameters like slope of the symmetry energy, or yeah, this symmetry, the energy difference between pure neutron matter and symmetric nuclear matter, and saturation density, which corresponds to this minimum, and incompressibility, which is related to this curvature. So yeah, how stiff or soft of equation state is. Yeah. Okay. So with terrestrial, experiment, accelerator facilities, we can study some part of properties of equation state. For instance, by studying the so-called blazing mode, which is isoscalar giant with monopole resonance, which contains, which is related to some density oscillation, of one nucleus, and since it changes the density higher and lower, it is this excitation energy is related to the incompressibility of nuclear matter. And also one can study the so-called giant dipole resonance, which is out of phase oscillation of neutron and proton densities. And in case of heavy nucleus like lead-208, we have some excess neutrons at the surface region, which is known as neutron skin. And yeah, this again, this excitation energy of ice vector giant dipole resonance can be related to the symmetry energy and this L parameter and so on. So in this way, using terrestrial experiments, we can study a bit about the nuclear EOS around the saturation density. But the problem is we cannot study experimentally this very low density region and higher density region. So we must rely on some theoretical EOS. But anyhow, so once we have this kind of energy as a function of density, the so-called EOS, we can readily calculate what's the mass and radius of neutron star. Okay. So how to do it? So here, I just remind you, so the EOS equation state is nothing but the dependence of energy on the density. And through this simple thermodynamic relation, we can get the density dependence of the pressure of the system. Okay. So by having the equation state, you can get this PM, the pressure. And then you can apply this pressure into the Truman-Oppenheimer-Bloch equation, TOB equation here. So this is nothing but the equilibrium condition between the pressure, outward pressure, and inward attraction of gravity. Okay. And if you look at this first part of this equation, it is just a Newtonian equilibrium condition. And these factors with this red underline is collection from the general relativity. Okay. And actually, this equation is just the differential equation. We can solve it easily numerically. So by putting some initial condition, let's say the pressure or density at the center of neutron star, we can solve this equation step by step outward from the center of neutron star towards the outside of neutron star. Okay. So since we know this PM, the density dependence of the pressure, by solving this Truman-Oppenheimer-Volkoff equation, we have pressure at certain distance or radius, and then we can convert this pressure into density. Okay, and actually this right-hand side is can be calculated, and we can go to the next step, and we can repeat this step-by-step iteration until the pressure becomes 0, and it defines the surface of the neutron star. So in this way, we can get what is the surface or radius of the neutron star, and we can integrate what is the mass inside this neutron star. We can get the so-called mass radius relation. Okay, so this is the mass and the radius of neutron star calculated with various equation states. So since we have many equation states, there are many lines. Okay. And so for a given equation state, we can draw one single line like this. Okay. And the point is, we have observational constraints like gravitational wave detection, which provides this upper limit of neutron star mass. I mean, yeah. And there are several new observations of mass and radius of neutron star. And the point is, we should explain those observations. In other words, the equation states that cannot reproduce those observational constraints, those equation states are unphysical, or we can exclude those equation states. So in this way, we are trying to constrain more and more the equation state and what is the nuclear matter properties through the comparison between mass and radius relation and the observation. So this is one of the hot topic of neutron star study. Okay, and then okay, so I just explained how to solve the TOB equation. So yeah, but I will go quickly, probably. So here I just rewrite a bit the TOB equation through this condition. Using a chain rule, yeah, I replace the left-hand side d and dr, and I just moved this factor to the right-hand side. And okay, for instance, we have scan energy density function. So as I introduced, we can apply an effective density-dependent nuclear interaction and use the theta determinant to take the expectation value. And it provides us some kind of energy density function. And it is actually regarded as an EOS. So we can use the same parameter set that was used to describe the finite nuclei and nuclear reactions and so on. And we can calculate what the energy and the pressure and solve the TOB equation. And those are just definitions. So baryon number densities is just a summation of neutron and proton number densities. And Yp is the so-called proton fraction defined by this. And we have neutrons and protons and lepton gas, relativistic lepton gases. Yeah. And through the nuclear interaction, we have this nuclear energy density function, which is related to this equation. So you have all the information to solve the TOB. And yeah, this is just how to proceed. So you can, for instance, you can define what is the central density. Okay. Then you can find what is the Yp, proton fraction, through the beta equilibrium condition. And yeah, but at the same time, you have to require the charge neutrality condition. Okay. So by putting some prior Yp, you can calculate what is the chemical potentials of neutrons and protons. And yeah, through the beta equilibrium condition, you can get what is the chemical potential of electrons, and it is related to the number densities of leptons. And you can check if this condition is satisfied. And then, yeah, you can repeat this procedure to determine what is the proton fraction that satisfies beta equilibrium and charge neutrality conditions. And after defining the Yp, you can calculate the mass density. Since you have compositions, you can calculate each terms, nuclear and leptonic part of the energy density, and you can calculate the mass density and the mass coordinates. And you can repeat this procedure step by step, for instance, using a Runge-Kutta algorithm to solve this equation, and you can draw this mass radius relation. Okay, so those are just an example. So, for instance, this is the chemical potential as a function of central density. Okay. So when we change the central density, the chemical potential changes like this. Okay. So neutron and protons chemical potential are much larger than electrons one, and it grows with density. And though this figure shows particle fractions, so the red line shows the neutrons fraction. So it is nearly 1 at the low density region, but it becomes smaller, a bit smaller. And proton fraction and lepton fractions increases like this. And okay, so by solving T of equation as a function of radius or radial coordinate, we can get this kind of density distribution. So this shows the density distribution of the neutron star. So starting from those initial central density, we can solve outward the T of equation, and depending on the central baryon density, number density, we have this density distribution, and this shows the pressure. But in this way, you can calculate mass radius relation. But okay, so I didn't update those calculations, and those are some preliminary results. So, but more or less, it is what we can obtain using some scan type energy density function. Okay, so now in the rest of 30 minutes or so, I will discuss some specific layer of neutron star. Okay, so I will discuss the inner crust, and especially at the bottom layer of inner crust, some peculiar phase emerges. Okay, which is the so-called nuclear pasta. Okay. So what is nuclear pasta? So it is something like this. Okay. So at the bottom picture, it shows some theoretical calculations of structure of the inner crust, I mean bottom layer of inner crust. So those orange colored area, regions corresponds to nuclear matter with neutrons and protons. And outside of this orange region, you have some electron gas and triple neutrons. Okay. In the low density region, you have some cluster of nuclei which form some Coulomb lattice. Okay. And it is similar to gnocchi. Okay. And as we go higher in density, the lattice, distance between those gnocchi or clusters decreases. And at some point, the Coulomb repulsion is increasing, and system choose to merge like a rod. Okay, so by changing the shape from the cluster to some kind of rods, it can reduce the Coulomb energy. But as you can see, the surface of this nuclear matter increases. So nuclear energy is somehow reduced. But through the competition between nuclear attraction and Coulomb repulsion, we can have this kind of structure, rod-like structure. And this is related to, similar to spaghetti, you may see here and here. And if we go higher in density, at some point, okay, so those rod-shaped nuclei are merging to form kind of slabs or lasagna structure. Okay. And actually, those, higher density regions, we have anti-spaghetti and anti-gnocchi. So it is some kind of, opposite, or how to say, like a Swiss cheese or, it is like a hole inside the uniform matter. And those holes form a coulomb lattice. While in this anti-spaghetti region, some tubes are created. So inside the uniform matter. So densities are flipped between this gnocchi and anti-gnocchi and spaghetti and anti-spaghetti. So anyway, some people started to call this kind of structure as nuclear pasta, and nowadays everyone calls this as nuclear pasta. Okay. So the point is those structures are like a crystal or solids. And this is the kind of infinite system. So we should use the band theory of solids to correctly describe this solid state of nuclear matter. Okay, so here I just remind you some part of band structure in solids. Okay, just naively and quickly I will go. So here I drew some electrons energy level of some single atom. Okay, assume it is like this. And if we bring another atom close to this atom here, you will have two levels, two energy levels close to each other. And it is related to anti-bonding and bonding and anti-bonding molecular orbitals. Okay, something like this and this. And you can continue this further and further. So 3 atoms, 4 atoms, and many atoms. Okay. In the end, you will have kind of a dense band of electron energy levels. It is like a band. So we can repeat or consider similar formation of energy bands as a function of interatomic distance. Okay. So when interatomic distance is very large, those atoms are isolated. So we will have just a single energy levels. But as the interatomic distance decreases, we have formation of molecular orbitals, and we will have this kind of energy bands depending on this interatomic distance. And okay, the system chooses the most energetically favorable distance. Okay, this defines the molecule or solids. And assume that this electron orbital was filled, and this orbital was empty. Okay, so this was the highest occupied atomic states. And in such a case, depending on the optimal interatomic distance, we will have different properties like insulator or conductor. So for instance, when we have, so this orange dashed line, so if the optimal atomic distance was here, then as you can see, we do not have any band gap. So the situation is something like this, and electrons at this Fermi energy can freely conduct. So it is inside the conduction band, so it behaves like a conductor. But on the other side, if we have a band gap here for this interatomic distance, so the field valence band is somewhere here, up to here. And to excite the last occupied electrons, we need to add some energy to overcome this band gap. Since it is, difficult, it behaves like an insulator. And in between them, we will have the semiconductor. Okay. So anyway, those are just a basic reminder of what is a band theory. So now recently, we are developing some kind of time-dependent band theory based on time-dependent density function theory to describe band structure of the inner crust. So when I was in Niigata University with master's course student, we published this article. So this was a time-dependent band theory for the slab phase of inner crust. And recently, so this is very recent, in this year, with Yoshimura-kun, he is the first year PhD student in my group. We developed a superfluid extension of time-dependent band theory. Okay, so those are students and one professor in Niigata University. And nowadays, Yoshimura-kun, he got a JSPS fellowship, this one, and he did already the superfluid extension and also finite temperature and finite magnetic field. So we are now developing fully microscopic band theory to describe everything inside the inner crust, including the band structure effect. Okay. So I will just introduce, what we are discussing in those papers. So the main point is the finding of anti-entrainment effects. Anti-entrainment effects. Okay. So let me first explain what is the entrainment effect inside the inner crust of neutron star. So what is entrainment? So if you look at the dictionary, entrainment is defined as a phenomenon between two species, any particles or gases or fluids and so on, and a motion of one component drag or affects the other. So this is the definition of entrainment. Okay. So we can find this kind of phenomenon in daily life. So this guy is attracted by the other component. And in case of inner crust of neutron star, sees neutrons, and this guy is protons. Okay. But actually, we consider the band theory. So the situation becomes a bit complex. So these protons forms a cluster, okay? So there is a bound neutrons. So those are nuclei or some particle structure. So this is due to attraction of protons and neutrons. And actually, in the inner crust, we have drift free neutrons, which is actually in the superfluid phase. And these free neutrons actually affect the clusters through the band structure. So this is the situation. So here I depict the situation. So the entrainment effect in the inner crust. So here I draw these blue lines to express the potential, mean field potential for neutrons. Okay. So because of the proton-neutron cluster, we have this kind of mean field potential. And inside this potential, we have discrete energy levels. And those are bound state of neutrons. And so those bound neutrons are localized around the cluster. So wave function is localized. But in addition to this, we have drift neutrons, inside the inner crust. So those drift neutrons are not trapped by this potential. So those are kind of free neutrons. But because of this formation of periodic potential, we have to use the band theory to correctly describe the system of neutrons inside the periodic potential. So now, because of the band structure effect, there are some neutrons which are effectively immobilized or effectively bound to this cluster structure. Okay. So those are entrainment effects. So those neutrons are entrained by those periodic potential. So now we can quantify this entrainment effect by taking a ratio between this number density of drift neutrons and number density of conduction neutrons that can actually flow, that can actually conduct. Okay. So by taking the ratio, we can define kind of effective mass, the so-called macroscopic effective mass. Okay. So anyhow, when entrainment effect is strong, the conduction neutron number density is reduced. Okay, because of strong entrainment. So in such a case, we can regard that the neutrons have larger effective mass. So it means the neutrons are hard to flow, difficult to flow. So anyway, so this is the entrainment effect, which is related to the effective mass of drift neutrons. So this kind of discussion is related to various phenomena of the neutron star. So one is a neutron star glitch, pulsar glitch, which I will introduce in the next lecture. And the other one is the so-called quasi-periodic oscillation, QPO. So what is this? So this is actually the oscillation of star, neutron star. So in some cases, the neutron star has some explosive event, the so-called gamma ray burst. And by observing this neutron star after the gamma ray burst, one finds that it oscillates in time and it decays. So this is like a star quake, the oscillation of neutron star. And by analyzing this oscillation pattern by using the Fourier analysis, we know that there are some characteristic frequencies in this oscillation. So it must be related to the structure of neutron star. And this is some analogy of seismology. In Japanese, it is Jishingak. So we cannot go inside the Earth, okay? But by analyzing the propagation pattern of the earthquake, I don't know the detail, but one can study what is inside of the Earth. So this is the seismology. So we can consider a similar thing for the neutron star. So using QPO, quasi-periodic oscillation, we can consider kind of asteroid seismology. Okay. So this paper was published in 2019, okay, quite recently, and by Japanese researchers. So what they did, so they consider kind of pasta structure and some oscillation mode of nuclear pasta. As you can see, as a lasagna sandwich. It is some, it is not realistic food, but you may consider this kind of sandwich or pasta structure. Then what they did, so they found that there are actually 30 observed QPO frequencies, and in addition to that, there are some Bayesian analysis predictions. And actually, they could reproduce those characteristic frequencies of QPO using this model, lasagna sandwich model. Okay, so it is, yeah, kind of strong evidence of existence of nuclear pasta inside the neutron star. Okay. However, yeah, the interpretation could be affected by the entrainment effect. So because, so they don't know the details of the, microscopic, yeah, ingredient of the pasta structure, especially the band structure effect. And if the band structure affects strongly the dripped neutrons or the mass of the pasta structure, let's say, it can affect the frequencies and interpretations. So this kind of things should be resolved based on the microscopic calculations. Okay, so now I will just mention here what we did. So what we should do is to introduce the so-called Bloch boundary condition, which we may learn in the solid state physics. So the point is the wave functions, single particle wave functions, has the periodicity of the potential. So in case of slump phases, okay, then we have only, in this picture, XY direction, it is uniform. And in the Z direction, we have a sequence of slabs. So in such a case, the wave function has periodicity or along the Z coordinate. So after A, in the period A, we have appearance of same slab structure. So we impose this periodicity to the wave function, and we solve the Constant equations and do the calculation. So yeah, I skipped the details, but we can formulate the Constant equation and time-dependent extension based on this boundary condition for the solid states. Okay, here I just show some example. The left figure shows the density distribution of neutrons and protons. And this bottom panel shows the mean field potential. And in this case, the proton fraction is large, so we do not have dripped neutrons. And on the right-hand side, I show neutrons' single particle energies as a function of Bloch wave number. So this is related to the crystalline structure. Actually, this is the so-called first Brillouin zone. But anyway, but in this case, those are bound orbitals inside the potential. So those single particle energy do not depend on the Bloch wave number, meaning that they are localized inside the cluster. So, okay, so those bound neutrons are not affected by periodic potential. On the other hand, if we increase the number of neutrons or reduce the proton fraction, then we will have these dripped neutrons outside of the slabs, and potential changes like this. So protons' potential is much deeper because of the excess neutrons. Yeah. Okay. So in this case, since you have dripped neutrons outside the slab, you have occupied neutrons even outside of the nuclear potential. And in this case, in those cases, you have some single particle energy levels, which depends on the Bloch wave number here. And thus, those are the so-called band structure. Okay, I skip this. And what is the point? So now, since we employ the time-dependent density function theory with Bloch boundary condition, we can do some, numerical experiment or calculation. So what we did, so here is the image. So here we have the cluster. In our case, that was slab structure. But okay, anyway, we have some new cluster of neutrons and protons. And outside of the cluster, we have drift neutrons. And we exert an external force here, which is constant in time. Then you can calculate the time evolution. And you can classically, naively expect that this cluster will show constant acceleration motion. Okay, so this is the velocity as a function of time. And this is constant. And by measuring this acceleration, and you can calculate the expectation value of time derivative of linear momentum, you can calculate what is the mass of this cluster. So in this way, based on the time-dependent band theory calculation, we can calculate what is the mass of the cluster. Okay, I will skip this. And so it is related to the entrainment effect. So this mass of the cluster quantifies the bound neutrons and entrained neutrons. Okay. So by analyzing the cluster mass, we can, on the other hand, access the conduction, what is the conduction neutron number density. That was the idea. So using this kind of technique, we could quantify what is the entrainment effects in this slab phase of neutron star pattern. Okay, I have only 5 minutes. Okay, so I may say few words here. So this is the most important figure. So by analyzing this acceleration, we can deduce what is the slab mass of the slab, and I take a ratio between number of bound neutrons, which was calculated by looking at the energy. So we have this kind of potential, and we can count number of neutrons which may be bound as a function according to the single particle energy. So I took the ratio, and as you can see, so for lower density region, I mean when we have almost no drift neutrons, this ratio becomes 1. Okay, it shows this kind of picture is correct. But when we have drift neutrons outside of the slab, it becomes much lower and lower. So actually, the mass of the slab is reduced because of the band structure effect. Okay, so I just say a few words about the origin. Okay, I will skip this. And the most importantly, it is what we call anti-entrainment effect. So what is this? So here I plot the proton's current density. Okay, current. So this red color means it is positive. Okay, as a function of z coordinate and time. So we evolve it in time, and then protons start moving towards a positive z direction, a direction parallel to the external force. So as expected. But on the other hand, if he plots the neutron's current density, actually we found that the drift neutrons start flowing opposite to the external force. Which we call anti-entrainment effect. So this is due to the band structure effect. So actually, the effective mass macroscopic effective mass is related to the curvature of the band, energy band, as a function of Bloch wave number. So depending on the curvature of the band, the macroscopic effective mass can change the sign. So some neutrons, drift neutrons, may have negative effective mass. So it responds to the opposite way to the external force. And in this way, the system reduces the this linear momentum and its time derivative. It reduces the mass of the slab. And actually, it means the conduction neutron number density is enhanced, actually, because of the band structure effect. So, which we call anti-entrainment effect. And okay, in the rest of 2 minutes, okay, I will skip the detail, but we have extended it to include the superfluidity using the HFB, and I can skip this. So in the end, okay, in the end, what we found is the superfluidity is not significantly affected the anti-entrainment effect in the end, but slightly enhance the anti-entrainment. But anyhow, so we could do the such extension. And here I will just show finite temperature extension. So what is this? So I can skip. For instance, okay, here. So here I show our calculation with different temperature, 1, 3, 4, and 5 MeV. And as temperature increases, as you can see, the slab is melting, and finally it becomes uniform. So in this way, we can use the microscopic band theory, including superfluidity and temperature effect, to describe what's inside the inner crust. Okay, then I will summarize soon. Okay, so our future goal is, yeah, yeah, we have developed such a microscopic framework to describe the properties of inner crust, and we can nowadays tune what is the temperature and magnetic field externally, I mean in the calculation, and we can predict many things based on the theoretical calculations. And if we can do such a thing, this is some view of future study. But okay, after the supernova explosion, we will have a formation of hot protoneutron star, and it gradually, cools down through the neutrino emission. And as you can imagine, some superconducting transition should occur at certain temperature, certain critical temperature. So you will have this kind of situation, and also after certain cooling, the crust must be formed. So in this way, by analyzing, calculating many phases of inner crust of neutron star, or generally the structure of neutron star, as a function of temperature and magnetic field, we may predict something which may be observed in future. Okay, so this gives you this is last image. Okay, anyway, so it shows the animation shows the freezing bubble. Okay, but this gives you an image. So at hot environment, the neutron star was hot and there was no crust structure. But after some cooling, of course, neutrons and protons can become a superfluid and superconducting phase, but also crust region should be formed in some way. And we hope in some day we may predict what's going on during the formation and cooling of neutron star. Okay, and this is the summary of this lecture. So yeah, today I explained what's the basic physics of neutron stars, which related to mass and radius of neutron star and QPO and blah blah blah. And it is of course related to the physics of finite nuclei. So nuclear forces, nuclear structures, and it is, yeah, I introduced the equation state, yeah, which can be calculated as a nuclear many body problem. And in this way, those are mutually related. And of course, experimental study is important to constrain many properties of finite nuclei. And also observations are also important to put some constraints of mass and radius relation and some observations like gravitational waves and QPOs and glitches. Okay. So this is the summary of my lecture today. And if you have any questions, please ask. If not, please finish. Okay. Thank you.